Hello everyone, welcome to the series of lectures on the course Calculus and Numerical Methods. In this session, we are going to talk about the greatest integer function. Okay, so I have the statement with me. Let x be a real number, then there exists a unique integer m such that m is less than or equal to x and that is strictly less than m plus 1. So greatest integer functions you all must have studied in your lower classes. Okay, so for any real number, I can find an integer which is less than or equal to this, and that is this m. Okay, and this real number x is going to lie between m and m plus 1. Okay, so if I pick up any real number, let's say I pick up a real number x, then this x has two choices. Okay, either it is an integer, so that x either belongs to the set of integers, so it's an integer, or it is not an integer. These are the two choices for this x, real number x. So if I look at the case one, if I look at case one, supposing x is an integer. Okay, so if I draw the number line, and supposing these are my integers, supposing this is x and this is x plus 1, this is x plus 2, and so on, this keeps on moving, and I have integers on the left of x as well. So if x is an integer, so it is here. Okay, so I can choose my m to be x itself, right? So what we have shown, there is a integer m which is equal to x itself such that x is less than or equal to itself and it is strictly less than x plus 1. So if x is an integer, the statement which I have written here is making sense, right? Because corresponding to this x, I can find an integer m which is x in particular, which is x, which satisfies this condition, right? If x is not an integer, then I have case 2. Okay, if x is not an integer, then I have case 2. Okay, so let me put this also on the number line. So if x is not an integer, it is going to lie between two integers. Okay, so x is not an integer, so definitely it is going to lie between two integers. So I will call this as m and I'll call this as m plus 1, right? And this m is called the integral part of x. If it is not an integer, that means you only look at the integral part and you remove the decimal part. Okay, and then you come to m. And another notation for this is you put a box bracket and you write the number x inside it. That means I'm looking at the integral part of x. Okay, so if x is not an integer, then I will choose x as my integral part of x, and I'll choose m as integral part of x. Okay, so if this is m, then this is going to be m plus 1, and that is nothing but integral part of x plus 1. So again, I can find such a m such that this is going to be less than or equal to x, and that is strictly less than integral part of x plus 1. Okay, so if you take any real number, let's say 7.6, I can always write it as integer plus the fraction, and this is called the integral part and this is called the fractional part. Okay, and sometimes we also denote it as this: integral part of x is this and fractional part of x is this. All right, so no matter what real number x you take, you will always be able to find one integer m which will satisfy this condition. Okay, so let's prove this statement formally now. So for that, what I'll do is I have my real number x on the number line. Okay, x is some real number. I will look at all the integers which are less than or equal to x and I will form one set S. Okay, so consider the set S equal to all the integers I'll pick up which are less than or equal to x, right? Then can this set S be empty? Let's assume that S is empty and let's see what is happening. Okay, let if possible S be an empty set. That means there are no integers which are less than or equal to x. That means every integer is greater than x, right? Therefore, for every integer k has to be greater than x. So k is less than x for every integer x. This means x is the lower bound for z for the set of integers. That means z is bounded below. That's a contradiction. This means z is bounded below. We have already seen that z is neither bounded above nor below. Okay, so that's a contradiction. So why we are getting this contradiction? Because we assume that the set S is empty and hence S is a non-empty set. Okay, so I'll name this 1. So S is a non-empty set. This is what I know from this, right? So now if I look at the definition of the set S, which elements are coming inside S? All those integers k which are less than or equal to x, right? So k is less than or equal to x for every k in S. This is by definition of the set S. That means x is an upper bound for the set S because every element of S is less than or equal to x. Therefore, x is an upper bound of S, right? That means S is bounded above. And because x is a real number, it is bounded above in R. So from 1 and 2, what do we have? S is a non-empty subset which is bounded above in R. It's a subset of R because it's a subset of integers, and integers is a subset of real numbers, right? So finally what I have, therefore S is a non-empty subset of R. S is a non-empty subset of R which is bounded above in R. Right? That means it is going to have a supremum in R by the least upper bound property. So our least upper bound property tells us that by least upper bound property, there exists a real number R, alpha in R, such that alpha is equal to the supremum of the set S. Fine. So alpha is nothing but you can also say least upper bound of S. Alpha is the smallest upper bound of S. If alpha is the smallest upper bound of S, then anything less than alpha cannot be an upper bound for S. Correct? So alpha minus 1, if I pick up, this is a real number which is less than alpha. Okay. So since alpha minus 1 is less than alpha, alpha minus 1 is not an upper bound of S. And when do you say that a number is not an upper bound of the set S? When there is an element in the set S which is bigger than alpha minus 1. That means there exists one element M inside S such that alpha minus 1 is less than that element. Okay, so I'll call this statement as 3 statement. Okay, because I'll be using it later. So I'm referring it as 3. Okay, this M element is there in S, right? And if I look at the set S, it is having all integers which are less than or equal to x, and M is an element in S. That means M is an integer and M is less than or equal to x. Okay, so M is less than or equal to x. So this is what I know, right? So I have succeeded in finding an integer M which is less than or equal to x, and that is half part of my statement if you see here. So the only thing I need to show now is x is strictly less than m plus 1. If I show this second half, then I'm done. Okay, so I want to show that x is less than m plus 1. We will go by contradiction. So I want to show that, okay, I want to show that x is strictly less than m plus 1. Before that, I will name this statement as 4. So suppose not. Okay, so we will assume it's opposite. Suppose x is greater than or equal to m plus 1. By law of trichotomy, if the given statement, if this is false, that means this has to be true. Okay, so I'm assuming that m is bigger than or x is bigger than or equal to m plus 1. This implies another way of writing this is what? M plus 1 is less than or equal to x. Okay, that is m plus 1 is less than or equal to x. Now, and m is an integer, so m plus 1 is also an integer. That means this number m plus 1 is an integer and it is less than or equal to x. That means it satisfies all the conditions to be in the set S. Okay, and this tells me that m plus 1 is there in S. Correct? But alpha is the supremum of S. That means every element of S must be less than or equal to alpha. Okay, but alpha is the supremum of S. This implies m plus 1 is less than or equal to alpha. And so what I'll do is I will transfer that one on that side, on the other side, and that will give me, so this gives me m is less than or equal to alpha minus 1. This is a contradiction to, here we are saying alpha minus 1 is strictly less than m in 3, and now I'm saying alpha minus 1 is bigger than or equal to m. So this is a contradiction to the statement 3 that we had done earlier. So this is a contradiction to the statement 3. We're getting this contradiction because we assumed that x is bigger than or equal to m plus 1, and therefore x is strictly less than m plus 1. I'll name this as 5. Yes, I'll name this as 5. And finally, by 4 and 5, what do I have? M is less than or equal to x, and that is strictly less than m plus 1. So we have succeeded in finding an integer m such that m is less than or equal to x, and that is strictly less than m plus 1. All right. Now we need to show that the integer m that we have obtained here, this m, is unique. Okay, so because that's what a statement says. So if you go back to the statement, it says there exists a unique integer m such that m is less than or equal to x and x is strictly less than m plus 1. Okay, we have found an integer m. Now only thing is that is left is to show that m is unique. Okay, so how we show that an integer is unique? We will assume that there are two such integers which satisfy this condition, and we will show that both those integers are equal to each other. Okay, that is the standard way of showing that two things are unique. Okay, so let's do that. So my claim is m is unique. Okay, so I'll assume that there are two integers. Suppose there exists integers m and n such that m also satisfies this condition and n also satisfies this condition. We need to show that these two numbers m and n, these two integers m and n are unique. Okay, that means we have to show that m is equal to n. If you have two such integers, then they are equal to each other. Okay, so we will go by contradiction here. I'll assume that m is not equal to n. Okay, let if possible m be different from a. So what are the two choices for m and n now? Either m is strictly bigger than n or m is strictly less than n. Okay, so what I'll do is I'll assume one of them and I will prove that I'm getting a contradiction. I'll arrive at a contradiction, and you can also try the second one and you can also get a contradiction in a similar way. Okay, so without loss of generality, I'll assume that without loss of generality, that means I'm not creating harm to anyone. Okay, I need to assume one of them, one of these two statements. So I'll assume one of them, and similarly we can do the same thing for the other case as well. Okay, so without loss of generality, I'll assume that m is strictly less than n, any one of them. Okay, so I'll assume this one. So I'm assuming that m is strictly less than n. Now m and n are two integers, so I'll just put them on a number line. Supposing m is my integer here. So what are the possible choices for this n? Okay, n is an integer which is greater than m. So n can be m plus 1, or it can be m plus 2, or it can be m plus 3, or it can be any integer after m plus 3 as well. That means the number n that is here, n is strictly greater than m. It can be bigger than or equal to m plus 1. It cannot be less than m plus 1. Okay, so note that n is greater than or equal to m plus 1. Okay, because it has to be an integer this side. So these are all the choices for n that are possible. Now if I look at this condition, okay, this assumption, okay, so now I know that m is strictly less than or equal to x and x is strictly less than m plus 1, and from here m plus 1 is less than or equal to n. So I will use this inequality here, that is strictly less than n, sorry, less than or equal to n. So from here what I have is x is strictly less than n, right? So x is strictly less than n. That's a contradiction because we assume that n is less than or equal to x, and now I'm getting x is strictly less than x. So I'm getting the opposite of what I'd assumed. Okay, so this is a contradiction. We are getting this contradiction because we assumed that m is not equal to n, and therefore m is equal to n. So if you assume that there are two such integers which are satisfying this condition, then both those integers are equal to each other. Okay, and therefore we conclude that m is unique. So there exists a unique integer m such that m is less than or equal to x and x is strictly less than m plus 1. Okay, and this m what we have here is nothing but the integral part of x. Okay, as I explained in the beginning of this video, if I have x here, okay, so the integral part of x is here and integral part of x plus 1 is here. So this is nothing but your m and this is nothing but your m plus 1. So x, if it is an integer, it will be equal to this m and it will lie here, and that's when m can be equal to x. Okay, but x is always strictly less than m plus 1. Okay, and this m is called the integral part of x. All right. So this was the greatest integer function, and these are my references. Thank you.